In part 2 of Module 6, we're going to continue our discussion of entropy, and we're going to look at entropy in a more general way, and then we're going to look at important thermodynamic relations that we can use for a simple substance. So the first thing I want to do in this part is to sort of define what entropy is and how we can understand entropy at more of a molecular level. So as we said before, entropy explains the second law and it defines a direction for the energy flow. But that doesn't really help us in understanding what it is and how it actually works. So let's try and look at how we can define entropy and define it a little bit more on a molecular level. So the first thing I want to do is draw two beakers, and one is going to have water at 20 degrees. Okay, so water at 20 degrees, and the other beaker is just going to have ice cubes throughout. Okay, and the ice cubes are at like 0 degrees Celsius. And the question is, which one has more entropy? Is it the water at 20 degrees or the ice? Well, the water has more entropy. So the water at 20 degrees has more entropy, and therefore the ice has less. And what we can say about ice and water is that for ice, the molecular structure is more bound together. Okay, so we have a molecular structure if we look at the ice cube that is more bound together, and we also know from this that we have a lower temperature. Okay, if something is more bound together, we have a lower temperature. This is how we can actually look at temperature at a molecular level. If things are closer together, they're usually at a lower temperature. Okay, so let's consider two different solids. Let's now look at, so we've defined that there's less entropy in ice, more entropy in water, and it seems to be related to temperature. Now, let's look at two solids, and we can call these solids A and B. And we're going to look at their molecular structure really, really close. So we're going to have this solid A on the left and solid B on the right. And this solid A is going to have a molecular structure that looks like this. So it's going to have 3 bonds like this, and it's also going to have 3 bonds in this direction. So it's different molecules put together that have some bonds. And in those bonds, so we see that there's 6 bonds total. And we know that there's some energy in each bond. Okay, we know that we have a certain amount of energy in each bond. And the energy can be shown as these little lines. The little green lines show us that the energy is spread out through the 6 bonds. Okay. Now, if we look at system B could have the same amount of energy, okay, could have the same amount of energy through the system, so it's a different system, and both systems have the same amount of energy, but B has the energy all piled up on only 2 of the bonds. So most of the energy is through 2 of the bonds. Okay, so we have energy is concentrated here. Okay, so they have the same energy, but the energy is concentrated in B. Now, entropy, what entropy means is, or what entropy can be thought of as, is entropy is the measure of the spread of energy. of the spread of energy. And that means that in our case, we would agree that our A has high entropy and B has low entropy. So essentially, if the energy is very concentrated in one spot, we have low entropy. Once the energy spreads out in a system, we now have a higher entropy. Okay, so we start with a low entropy and we go to a higher entropy as it spreads out. Okay, so this means low entropy means concentrated, and high entropy means spread out. And what we can also write from this is, what we can conclude from this is that energy is only useful when it is clumped together. So we're only interested in systems that have very low entropy and go towards high entropy. Okay, if we have a very low entropy and the energy is clumped together, we can use that energy to spread it out. Okay, and by spreading it out, we're doing some useful things. Okay, so that's the conclusion from this. So from a molecular point of view, you can now understand what entropy is and sort of how it works. Okay, so this was a little introduction to this part 2, just to make sure that we understand what entropy is on a molecular level and look at it from a little bit of a different angle than the definitions that you usually have for entropy, which are disorder or order, and it doesn't really make complete sense. So hopefully this makes sense. So if we have, for example, a hot cup in our room, which we've used as an example before, we have, if we look at the cup in the room, we have a low entropy, and then the entropy increases once the cup starts exchanging with the room and all the temperatures are spread out. So the energy from the coffee cup or the hot tea cup or whatever will expand to the room completely. Okay, so the next thing I want to do is let's try and put some equations into practice to use for a simple compressible substance. So let's look at two important relations. For a simple compressible substance. And these equations are called the Gibbs equations. Okay, so we're going to derive the Gibbs equations. So I'm going to write down the equations and then we're going to derive them to sort of understand where they're coming from. So the equations that are useful are that TdS is equal to du plus P dV. And our second equation is TdS is equal to dH minus V dP. Okay, so this is equation 1, equation 2, and they're called the Gibbs equations. Okay, so let's try and derive them. So let's derive the first one. So the first one is actually pretty easy to derive, but if we look at the first law, we can say that the first law we know is usually equal to the change in Q minus the change in work is equal to the change in U. Let me just rewrite the U. The change in U. And we're going to neglect delta PE and delta KE for now, just for the purposes of a problem. In most problems, we have this system. And what we're going to say in this first law is that if we have a quasi-equilibrium, so all the systems that we've been studying are quasi-equilibrium, and we also have a reversible process. So our process is reversible. We can say that we know that we can rearrange this equation to say dq is equal to du plus dw, okay, just by rearranging. And we know that dq from our definition of entropy is actually equal to T ds. So we can say that TdS is equal to du plus p dv. And we substitute for d work, we put p dv there to substitute. So we have TdS is equal to du plus p dv. First equation solved. Now, our second equation is derived by the definition of enthalpy. Okay, so we just derive this, we can derive the second equation from enthalpy. So let's say we have H is equal to U plus PV. Okay, this is our definition of enthalpy. Okay, then we can say if we differentiate this, we have that dH is equal to du plus, with the chain rule, we have plus pdv plus v dp. And if we go further than this, we can say that du, just by rearranging, is equal to dH minus pdv minus v dp. And if we plug that back in to our equation here, we can just plug it into our equation and we find our second Gibbs equation, which gives us TdS is equal to dH minus VdP. The PdVs cancel when you plug into that equation. So we have these two equations that are stem from this. Now, we can also write the equations in terms of their specific values. So we can say TdS with a small s is equal to du plus pd of specific volume. And we can say that TdS is also equal to dH minus v dp. Okay, so we can write the equations just like this if we want to as well. Okay, so those are the two ways to write the equations. And now what we're going to do is we're going to try and apply these equations to solids and liquids, and then we'll look at how to apply them to gases. So we'll have some form of understanding what the change in S is for solids and liquids and for gases as well. We already know how to find delta S for water and R134A. If we're given a question, we just use tables. Okay, we can use our tables. If we don't have tables, then we have to use these analytical relations from the Gibbs equation to solve for solids and liquids. So let's try and look at entropy change for solids and liquids first. So we remember for solids and liquids, we have that Cp is equal to Cv is equal to C. Okay, we just assume that Cp and Cv are the same. And we remember for our solids and liquids, we have U2 minus U1 is equal to H2 minus H1, which is equal to C T2 minus T1. Okay, and that means that dH is equal to du is equal to C dt, if we look at it in differential form. Now, if we apply this to our TdS equation, we can say TdS is equal to du plus pdV. Okay, so we have this relation. Now, pdV in a solid and liquid, we can assume that dV is going to be equal to 0 for liquids and solids. The reason why we can say it's 0 is because we usually assume that solids and liquids are incompressible. Okay, so we have that TdS and it's a lowercase s is equal to C dt. Now that we can substitute for du, we're just going to have C dt. We know that du is equal to C dt plus 0. Okay, we are canceling out our pdV. So now if we integrate the whole equation and bring the t to the other side, what we can do is we can say ds is equal to C over t of dt, okay, just from the definition and moving the t around. And then we can integrate both sides. And we're going to integrate both sides between 0.1 and 0.2 in a process. If we integrate both sides, if we have a constant CV or a constant CP, we're just going to call it C here. We're going to have C is outside of the integral, and then 1 over t integrated is ln of t from 2 to 1. So we have that this is equal to C ln of t2 minus C ln of t1. And from a logarithmic rule, we remember that the natural logs can just divide t2 by t1. So we're left with s2 minus s1 is equal to C times ln of t2 over t1, and that's our equation that we can use for S2 minus S1 of liquids and solids. So very simple equation to use. If we know the temperature at 1, temperature at 2, and we use C, we can find S2 minus S1. Now this C, remember, is C average. So it's the average between temperature 1 and temperature 2. And you can find C average in table A3. Now that we have an equation for solids and liquids, let's look at what we can do for entropy change for ideal gases. So let's look at entropy change for ideal gases. And for ideal gases, we can't really use this assumption that we have CV is equal to CP is equal to C. So we actually have to separate them, and we're going to come up with two different relations that we can use. So we have that du is equal to Cv dt, and we have the dH is equal to Cp dt from our definitions of the change in U and the change in H. And based on that, we also know that in ideal gases, we have PV is equal to RT. Okay, these are our three equations that we know from scratch. And now if we start with our relation, our TDS relations, or our TDS for the first TDS equation, we have TDS is equal to du plus P dV. And we can now adjust this equation by substituting for du, and we're also going to substitute for pressure. So we know that pressure is equal to RT over specific V if we rearrange the ideal gas equation. So we're going to be able to write that TDS is equal to Cv dt plus RT over V dV. And the reason we do this is because we're going to have to integrate the dV equation. So we try and put dV in terms of V. That's why we're substituting for the pressure. And we can therefore write, if we now bring the T over to the right side and divide everything by T, we have Cv over T dt plus R over V dV. Okay, and you can see how the T canceled out in the second part of the equation. And now we can integrate everything. So we have integral from 1 to 2 of Cv over T and integral from 1 to 2 of R over V. And the R comes out of the bracket, the integral, the Cv comes out of the integral, and we're left with, if we compute this integral, we're left with S2 minus S1 is equal to the integral from 1 to 2 of Cv dt over T. And we're going to leave it in integral form because Cv may or may not be constant, okay? Plus R times ln of V2 over V1. Okay, so we're leaving it in this form just because in gases, if we have very high pressures or very different values for temperature, Cv may or may not be constant. Okay, now the second equation that we can write is from our TDS relations. So if we have Cv as constant, then we can compute, we can take the Cv out and we know how to do the integral of dt over T. If Cv is not constant, we need to have Cv in terms of temperature to solve. Okay, but so this would be your first equation for ideal gases. And this ideal gas equation can be used strategically when you have a change in volume, for example, or you know your Cv and you know your volume 2 and volume 1, for example. Okay, now the other equation is derived from the other relation. So from TDS is equal to dH minus V dP. And we can do the same type of process here where we actually convert now volume into a pressure term, and we're left with ds is equal to Cp dt over T minus R dP over all over P. And if we integrate both sides, we get that S2 minus S1 is also equal to the integral from 1 to 2 of Cp now times dt over T minus R ln of P2 over P1. Okay, so this is our second relation for ideal gases. And both relations can be used for any problems. You're just going to choose the different equations based on, you're going to choose the different equations based on whichever you think is more appropriate for the problem, depending on what values you have. Okay, so they're both valid in any type of problem. So we'll call this equation 1, equation 2 in brackets, just so we have two different equations. Okay, if we refer back to them. And we can look at a quick example of what would happen if we had an isentropic process. So it's not really an example, but more of a showing what would happen if we had an isentropic process. So if we have an isentropic process, it means that delta S is equal to 0. We know there's no change in entropy in a process. And if we do have an isentropic process, we can say that the integral from 1 to 2 of Cp dt over T is equal to R ln P2 over P1. So we can use this equation to find that a definition for the integral of Cp dt over T is equal to R ln P2. Now, there are three different types of solutions for these equations. Okay, so we said there are three different types of solutions because Cp could be a function of temperature or could not be a function of temperature. So Cp could be constant or not, it depends. Okay, so let's look at the three different solutions that we could encounter to this equation. And by this equation, I mean the two equations for ideal gas. So the first one, the first type of solution is we have a constant Cp or Cv. And if we have constant Cp or Cv, we just find Cp or Cv at average temperature. And we take them out of the bracket, we take them out of the integral, and we just have the integral of dt over t, which becomes ln of t2 over t1. So in the case of this one, we have the following equations. We have that S2 minus S1, and these are lowercase, are equal to Cp average times ln of T2 over T1 minus R ln of P2 over P1. And the second equation is S2 minus S1 is equal to Cv average times ln of T2 over T1 plus R ln of V2 over V1. I'll just put brackets around all the natural logs just so we don't get confused. Okay, so it makes it very easy to solve for our problem now with Cp average, Cv average. Now, this is not always the best way because we're using an average Cp. So method 2 is to use an analytical equation for Cp of t. So Cp is now a function of t. And this can be found in our table A2C. So if we go to table A2C, so I'm going to go to table A2C just to show you, we have a table that shows us something that we haven't really looked at before, but it shows us the ideal gas specific heats of various common gases as a function of temperature. So this would be a way to solve for our, for example, if we have nitrogen, we could solve for nitrogen by plugging into this equation here. We would plug in A, B, C, D, and we would plug in our temperature values and we would get a value for Cp given at that temperature. Okay, so we could do it Cp for a certain temperature, Cp for another temperature, but we could plug that in to essentially our integral and then integrate with respect to temperature. Now, in this class, we're not going to do that. We're not going to actually solve for this because it would take too much time, but know that this technique is available to you if you want to. So we will not be using it, okay? So method 2, we're not going to be using, okay? Method 3 is using statistical thermodynamics. And using statistical thermodynamics, we can essentially come up with a value for Cp dt between 0 and a certain other value between 1 and 2, for example, that is going to give us what the value for the integral would be at every step, essentially. So we create this new term called S0, and we can say that S0 from 0 to t is equal to the integral of Cp t dt. So as a function of t, we can find an S0, or we can find a value for this integral for every temperature. And this is found experimentally, essentially. Okay, so experimentally, we can find what the S0 would be to solve for this equation. So instead of having the equation Cp average ln of T2 over T1, we can now use S20 minus S10 of the value. Okay, so we have that the equation now gets turned into S2 minus S1 is equal to S20 minus S10 minus R ln of P2 over P1. The important thing here is that we can use this for the Cp equation. We cannot use it for the Cv equation, okay? And the other problem with this is that in our textbook, we only have values for S0 for air. So we can only use this for air. Okay, so if you have different substances, such as nitrogen or something else, you would have to use method 1. For air, you can use method 1, or you can use method 3 if you would prefer to. So if we go to the tables for air, if we go to table A17, which is our table for air, in table A17, we can see that we are now given a value for S0 at different temperatures. So if we have our starting and final temperature, we can just use, for example, if our starting temperature is 300 and our final temperature is 320, we can use S2 minus S1, and that would give us our value for Cp ln of T2 over T1, essentially. Okay, so it's a little bit more accurate than using our Cp average, but you'll see that your values are very, very similar anyways. Okay, so we can go back and continue with our explanation. Okay, so the other thing we want to talk about is what happens if we have an isentropic process with constant specific heat. So what happens if we have isentropic process with constant specific heat? So if we have an isentropic process, we know that delta S is equal to 0, and constant specific heat means that we're going to have Cv average and Cp average within our equation usually. And so that means that we have, if we look at our initial equation, we can say S2 minus S1, and we'll use the Cp equation to start with, is equal to 0, which is equal to Cp times ln of T2 over T1 minus R ln of P2 over P1. And based on that equation, we can say that ln of T2 over T1 is equal to R over Cp. Okay, I brought the Cp over from the left to the right. R over Cp times ln of P2 over P1. Now, we can now write, if we have a natural log on the left and a natural log on the right, we can now cancel the natural logarithms. But in order to cancel the natural logarithms, we need to bring this as a power of P2 to P1. Okay, so if we bring the power over, then we can cancel the natural logarithm. So we're left with T2 over T1 is equal to P2 over P1 to the power of R over Cp. And we also know that R is equal to Cp minus Cv. That's the definition of R. So if we know that, we can say that R over Cp is equal to Cp minus Cv over Cp. And we also have the definition of K, which is the ratio of specific heats, is Cp over Cv. So this is the ratio of specific heats. Okay, it's a value called K. It's just Cp over Cv. Now, if we plug in K into here, we can say that R over Cp is actually equal to K minus 1 over K by doing some algebraic manipulation. And that means that we can say that T2 over T1 is equal to P2 over P1 to the power of K minus 1 over K for an isentropic process. We can also say that T2 over T1, if we do some further derivation, we could say that T2 over T1 is equal to V1 over V2 to the K minus 1. And we can say that P2 over P1 is equal to V1 over V2 to the power of K. Okay, just three different equations relating the different things for ideal gases for isentropic processes. So this is for isentropic processes. And the really interesting thing about this is that if you remember, this is a special case of a polytropic process. So if you look at this equation here, we can say that for isentropic processes, P V to the power of K is equal to a constant. A constant, not a constant. So PV to the power of K is equal to constant. So if you remember this, this is essentially a special case of the polytropic process where the exponent n is actually equal to K, which is Cp over Cv. So it's a special case. We'll write of polytropic where K is equal to n. Okay, so we've replaced n with K. And this, and all these equations as well, is valid for an ideal gas undergoing an isentropic process. We have now derived all the equations necessary to solve some example problems. So in part 3, we're going to be doing some problems on solids and liquids as well as ideal gases.